Okay, this isn't like the start of the class yet, but I received a query about this past year paper, 2017 question on lower bound. So actually I haven't exactly solved it yet. This is kind of like my first time putting it on paper, but let me see if I can, as in I thought about it, but haven't tried writing it out before. So consider an array of n elements, and suppose they are k distinct elements in 1 to n. So I imagine, so for example, if there are 3 distinct elements, for example, like, let's understand the question. Wait, my iPad froze. Oh no, what happened? This is not good. Oh no, my iPad froze. Oh no, okay, it's good, Okay, k distinct elements, so 3 distinct elements. So maybe there are like 5 elements, right? So what it means is that maybe it can be something like 10, 10, 20, okay, 22, 20, 20, something like this. So there are 5 elements, but there are 3 distinct elements. Oh, wait. Okay, I don't know if this means 1 to n or not. I forgot the notation, but the point is that there are 3 distinct elements and 5 total elements in total. So the lower bound, right? The usual idea for proving lower bounds would be to consider the decision trees. Something like the decision trees. But what you want to know is usually how many possibilities are there, like in the root. Sorry, in the leaves. Like how many possible leaves are there? How many possible outcomes of comparison are there, of sorting, right? In the case of sorting, normally it's n factorial, right? N factorial. But this time you're told that there are k distinct elements, right?
Yeah.
So that means that previously it includes all n factorials, but this time there are less possibilities because like for example 1, 1, and 2, right? Imagine sorting 3 elements, 1, 1, and 2. These 2 ones, whether you go on the left or go on the right, it's the same, right? So instead of like 3 factorial possibilities, now it's like let's see, now it's like less. Okay, thinking something like a radix sort. Yeah, maybe it can work. Actually, now that I think about it, maybe my idea is going not to be correct. K buckets. But we didn't cover radix sort. So maybe this question was, if it truly needed radix sort, then maybe it didn't, this is not under consideration, right? So let's see. Yeah, now as I'm talking about it, I realized there might be a flaw in my understanding, in my possible solution. But so my idea is like, I maintain contiguous like k buckets, and then I try to distribute. So there are n elements. So I try to distribute into these buckets. So this is like the outcome of sorting. Okay, to those who just came in, this is like, I received a question which I haven't exactly solved before, but I'm trying to see if I can do it on the spot now. We'll start at 403 like usual. Okay, so the idea is that find like number of ways to distribute n elements to k buckets such that each bucket has 1 element. Each bucket has at least 1 element. Okay, so yeah, this is what I was thinking along these lines. So okay, I don't know if I can go through this in 3 minutes. Let's see. So okay, so let me just clean it up a bit, right? So how do you distribute n items to k buckets any way you like? So there's this idea of like stars and bars. So the idea is that you imagine each bucket being like a partition, and then the elements are like you store elements here, something like this. Then you kind of like shuffle them around, like this is a possible partition. Then maybe this is also another possible partitioning. This is also another possible partitioning. Okay, so I need to look it up. I cannot remember exactly on top of my head what the result of this would be, but I think deriving it, if I have k plus 1, if I have k, so in total, right, here, there are n elements to consider, n elements, plus there are k things here, 1, 2, 3, 4. Okay, but because we are partitioning, so we add one more like bar into it, plus 1. So we have n plus k plus 1 things, and we choose n positions, choose where to put these n things. So I suspect the combination will be something like n plus k plus 1 choose n. Okay, n plus k plus 1 choose n. But this includes like a possible of an empty partition also. Possibilities that the partitions are empty, something like that. So the first thing you do is that out of the n elements, take away k first. Take away k, meaning every bucket already has one element inside it. Okay, then you plug it into this formula. Something like that. Wait, then I get, how do we get n plus k plus 1 again? So n plus k plus 1, okay, actually, how about I explain after class later, because it's about time to start. Okay, how's that? Yeah, I know that was a bit too fast because I kind of like did it on the spot and wasn't exactly prepared to answer that. But yeah, sorry about that. So, yep. So okay. Yeah, so check that you have archipelago invite, although I didn't really set up a lot of questions. Then do we have Google Doc for questions to ask me, is it? Like during the session? During the session or like throughout the semester? Oh, this session, yeah. So for this session, I think archipelago, I put up like a thing. Okay, it's a kind of like one-time answering kind of thing, but I did put up like, oh, anything you want me to go through in class. Google Doc for questions. Like questions you want to ask me during the class, right?
No, it's more like for consultation. Like, last in recess week you put out a Google Doc where we can fill out the because I was trying to find the link but I didn't find it, so I can't fill it out.
Oh, that was only for recess week, so I kind of like stopped asking.
Okay.
Yeah. Yep. So no worries about that. Okay. So anyway, let me set up my screen a bit first, because okay. So hi everyone. So today, oh yes, okay, Ishan, no worries. So yep, you didn't get, that's fine. There's nothing much in archipelago today anyway. It's like my custom tutorial questions, right? So yeah, it's week 7 and tomorrow is your midterm, right? So I started recording. Okay, hope everyone is fine. These are the things that I want to talk in class. So some administrative matters and 2 questions, 2D peak finding in linear time, and expected number of inversions. And the second question is actually last sem's midterm question. Okay. And then I had 2 extra questions I give also, and we can talk about it after class if you like. Okay. 2D peak finding is a question that you actually saw in past week tutorial, one of the weeks, but they gave like a m log n solution. So this time we want to improve it even further. Okay. So all right, this doesn't concern you. Right. I did not update this slide properly, but midterms is this Saturday, 11:30 a.m. Tomorrow, basically, 11:30 a.m. to 1:15. So take note, it's not 1:30, it's 1:15. Prof changed it to 1:15. So what happens is that your paper is 1.5 hours, starting from 11:30 to 1 p.m. And then for 15 minutes, you are given a time to like scan your answer and upload it to the thing. So do check your grouping. There are, I think, 7 or 8 breakout rooms. Check which breakout room you're supposed to go to. It's in the Luminous announcement somewhere. He sorted everyone by matrix number. And so you have to like binary search for your matrix number or something. Okay. So yep, find which group you're in. And I hope you know that week 1 to week 6 content. So I emphasize week 6 because we didn't have any tutorial on week 6 content. Except perfect hashing are examinable, right? Week 6 content not gone through me, but Prof did upload some like tutorial during the recess week, I think, like week 7 fingerprinting stream on Luminous. So do check it out if you haven't already. Okay, I think he's mentioned he should upload a video going through it, but I'm not sure if he really did. Okay, because I didn't see any announcements.
I think he uploaded a video last night. Yeah.
Oh, last night. Oh wow. Okay. All right. Sure. Yeah. So okay, this I think it's so close to midterms already, but I mean I don't answer like your content questions 48 hours before midterms because I have 4 midterms to prepare for. Before I help you guys, I need to help myself too. But if you have any questions like last minute logistical questions, like which group do you belong to, you still can ask me. Okay, that's fine. Okay. Right. So let's just begin with tutorial then. First question is 2D peak finding. Here's a quick recap of what the question is about. So we start with a 2D array of m rows and n columns, okay? M rows and n columns. And we call that a particular cell a peak if it's greater than or equal to its adjacent neighbors. Okay, so it can be equal, like 18 and 18 here, right? But if it's greater than or equal to all its neighbors, it's a peak. Okay, it quite makes intuitive sense. But our peak finding doesn't find like the best global peak. Any peak is enough. So even like this number 8 over here is a peak. Okay. Now let's recall like a key property for the OM log n solution is that this was one of the tutorial questions as well. Okay, so let's go through this slowly. The key property was that let this particular cell be the largest element in column J, right? In column J. So assume that the neighbors, assume that the other side, right? The other side has a larger element. So basically this guy is not a peak. There's something beside it that is larger, like 52 over here, for example. So we want to argue that in this subarray B, right? This any peak that is the largest element in its own column, like in this region, if it's a peak over there. So for example, let me see, yeah. So maybe this guy, let's say this is 100, right? Then this is like maybe all 0. Then I argue that if this is a peak here, that means it's also a peak here. Okay? Or maybe later I think there's like 80 over here. If it's a peak here, and it's also the largest element in the column, right? Then this guy is also a peak in the overall array, right? As you might have remembered last time, the problem comes when it's the border cases. So let's go through it slightly later. Okay. So any questions about like the question? Like need me to refresh on part because we went through this in the past tutorial. So I hope you somewhat remember. Okay. So I'll just wait for like 3 seconds maybe. Okay. Okay. So I'll go on. So case 1, easy case, right? So if like you consider the column J plus 2 onwards, this region, there's no contention. So like this guy over here, the 100, if it's the peak in this region, confirm it's still the peak in the entire thing, right? It's still a peak in the entire thing. So no problem here. The somewhat tricky part is that this guy over here, like a largest element in this column, if it's a peak, does that mean it's a peak in the entire array, entire matrix? So the analogy I gave the other time is that you are kind of like the best fish in your own pond, but does it mean that you're still the best fish in the entire ocean, like considering the entire matrix? Okay, that is the part that we needed a bit more work. So go through like the proof a bit fast, like because we did it last time, but refreshing again. So let's say like the important elements are these 4 elements, A, B, C, and D. So remember that the element B is the largest element in its column, right? In this column J, this is the largest in this column. So let's go through this slowly. The element D is larger than equals to C because it's the peak. It is the largest element in its own column. Like this is by our algorithm, we'll find this particular element largest in its column. That means D is greater than equals to C. Okay, so after that, C is greater than equals to B because of this property that we assume. Like assume the neighbors, the aij plus 1, this guy over here, C, is larger than equals to aij. This is the property that we are assuming. Okay. Then B is larger than equals to A because, well, aij, this element B, is the largest element in this column. So B is larger than A. So by transitivity, following all these inequalities, D is greater than equals to A. So D is greater than equals to A. We are sure that this guy will always be like a peak in the entire matrix. Okay. The algorithm is as such. So let's just focus on the recursive case. First, you find the middle column, find the middle, like the middle pillar, find the maximum in that single pillar. Once you find the maximum in that single pillar, you figure out, hey, are you a peak by examining its direct neighbors? It's not. If it is, just return it. Otherwise, if it's not a peak, means there's like a neighbor that is larger, right? Like either to the left or to the right that is larger. So you go to the side that has the larger element, or maybe both, but you go to like one of the sides that have a larger element. Okay. So this is recap, but any questions about this? Need me to recall, like re-explain some parts? Okay, can I get thumbs ups maybe? Okay, great. Okay, nice. So the next question is that, can we solve this in linear time? Okay, this algorithm I showed just now, we showed the other week, it's OM log n time, right? So the question is, can we solve this in linear time OM plus n? Okay, so I mean, I'm asking this, so definitely we can, but how do we do that? Okay, I'll like stop here for like maybe 10 to 15 seconds for you to like just quickly go through for those who haven't thought about it, but because I sent the answers to tutorial earlier, to the class group earlier, so you might have seen already. So if you haven't thought about it, think about it a bit, see how you can improve. Okay, I'll just wait first. Okay, so I'll go on. So here's an idea, right? So just now we divided by 2. Dividing the array by 2, like by column, right? It gave us a better solution from like, I think initially it was quadratic, mn, then we became m log n. So can we divide even further? We divided in like 1 dimension. Now let's try to divide in the other dimension. Okay, so instead of just dividing by columns, we try to divide by both the row and columns. Okay, so something like this, maybe. Just now it was just a single pillar, right? So maybe let's now have a plus only, right? So we divide by both the column and the row. Okay, then the algorithm sketch is as such. You find the maximum in this yellow plus. If it's a peak, return it, right? We found a peak. That's what we are seeking for. But if not, we do the same thing as before. One of its neighbors must have been like a larger element, right? So maybe like, for example, over here, let's say we have the number 10, then it's like 0, 0, 0, 11. So if it's not a peak because there's this guy 11 who's like blocking it from being a peak, we say, okay, let's focus on this sub-region. Okay, but so it sounds reasonable, but it's actually not a correct algorithm. Okay, so unfortunately we need a bit more work, but let me explain why this particular algorithm of you making a plus, just making a plus and then recursing like that will not work. Okay, so I showed this example earlier, right? There's the element 10. Let's say the element 10 is the max is the max in the plus. So this is the biggest guy. You can imagine everything else 0 maybe, for example, right? With the 9 here, this 9 will be important in a bit. I'll show you in a bit why it's important. Okay, so what we do is that our algorithm recurs to this region, submatrix, right? Okay, any questions so far? So this is our algorithm, like pseudo code, like very pseudo code-ish, right? We recurse to this subregion. Then what do we do in this subregion? We repeat the process again, right? We make a plus and then we find the max and then recurse if needed. So because I mean, it's a recursive algorithm. So we create a plus. Okay, I only have 4 elements. So just imagine the plus is like this. It's a bit off center, but that's because I don't have odd number of elements, right? But this plus over here is, I claim that this is going to be like, we can get a bad result if we just find the maximum on this plus. And here's an example. Okay, so let's say the plus only contains 8 0 0 0 0 0 0, right? So 8 here is the max. Okay, is the max of this plus. And then this number 8, right? Because our algorithm now examines, hey, is the number 8 a peak? Is the number 8 a peak? And then it sees its adjacent neighbors. Like, oh, 0, 0, and 0. Remember, we only focus on this region. So it doesn't know that the number 9 exists. Right? We focus only on this submatrix. It doesn't know the number 9 exists. It examines its adjacent neighbors. They are all zeros. So we say that, oh, 8 is the peak in this submatrix. Okay? But hopefully you see the problem here. Like the fact that there's a 9 over there. The fact that there's 9 over there means that even if this number 8 is the peak in this submatrix, it is not a peak in the entire matrix because of the number 9. So our algorithm fails because of this example. Is this clear? Was I too fast? Okay, so I'll stop here because like this is crucial to understand like what goes wrong with this algorithm. Okay, can I get thumbs ups? Okay, nice. People are understanding. That's a relief. Okay, so this is crucial. So what went wrong, right? What went wrong? The fundamental problem is that, notice that when we recurse into this region, this submatrix, we say we recurse because 11 was the culprit, was the reason we recurse into this submatrix. Okay, but then after we recurse to this submatrix, we kind of like just make a new plus without caring about the existence of 11. Like we don't really care that 11 was the reason. So that the fundamental reason is that this number element 8 is kind of like not exactly comparable to 11. Like we don't have any information to compare the two elements. Okay, so recall earlier, the reason we can say that this element D, this is the old algorithm, the haven't been linear, the M log n solution. The reason we can establish that D is a peak in the overall matrix is because of this like series of inequalities, right? We compare D with C, C with B, B with A. But this is not there yet in the new algorithm, right? Our goal is to be, ideally, we should be able to compare everything. D with C, C with B, B with A, right? So it's very similar to before, just that it's in the 2D setting. Okay, so you can compare everything, but alas, right? So this is our goal, but alas, we don't exactly have a way to compare D and C. We don't have any guarantees that D is actually greater than or equals to C. We can say that C is larger than B because that was the reason we recurse to this submatrix in the first place, right? That's fine. We can say that B is larger than A because, well, B is the biggest element in this plus. That's fine also. We are able to compare these two, but fundamentally, we are missing this relationship between D and C. That's why our algorithm failed. Okay, does this make sense? This is me just trying to formalize how come this doesn't work. How come it gave a wrong answer? Okay, so the new idea fixed is that instead of making it a plus, right, you also include these borders. Don't just make it a plus, include all the borders surrounding it as well. Okay, and I'll show you in a bit like why this will make it work now. Okay, so Okay, so let's say, right, after we find the maximum element over here in the entire, I call it the crosshair or crosshair, I don't know how it's pronounced, right? I just say crosshair, the crosshair allows us to, I claim that it actually allows us to establish a relationship between C and D. Okay, I think I don't have a slide on that. Okay, so I have to draw it out. So you can imagine, right, in the next recursive step, okay, let me go back one step behind. So B is the largest element in the yellow crosshair. Okay, C is the element that is larger than B that makes it become not a peak. Okay, it's not a peak because of C. So we recurse to this submatrix. Okay, our problem was that we were missing the connection between D and C. Okay, so this new crosshair, right? Because in the next step, we kind of like do so this is a bit of a bad example because it's very small, but you can imagine now I have a crosshair, right? And I want to find the maximum of the maximum element in this crosshair. And let's say it was D, right? If it was D that was the maximum, it must have been compared to C. Because of the way we define that it's a crosshair. So C has to be included in the comparison with D. So let me okay, I drew a 3 by 3 here, but let's say this is like a 5 by 5 instead. I think 5 by 5 might make it clearer. Okay, so this is the element D, this is the element C, right? So imagine this is B and this is A, something like this. Okay, so the crosshair is the yellow region here. Is the yellow region here, right? In the recursive call, in the smaller submatrix, we find the maximum in this yellow crosshair. We find the maximum in the yellow crosshair. And we say that, oh, I found D as the maximum. D is max. And that implies that because the D is the maximum in this crosshair, that means D is also larger than equals to C because C was also inside crosshair. Okay, so with this new like algorithm, it kind of fixes things. It fixes the fact that earlier we couldn't compare C and D. Earlier we couldn't compare C and D, but now we are able to because of the way we define our like the region that we take the maximum element from. Okay, does this make sense? Any questions about this? I'll stop here for questions. Okay, PM me if you have any doubts, but thumbs up please, otherwise. Okay. Okay, nice. Okay, nice. So I think people are understanding. If you don't, just feel free to PM me. I can repeat this again. Okay, so 1 second, yeah. Okay, nice. So now okay. So we have the algorithm already. So basically just modify it to find the maximum in the yellow crosshair, then do basically a similar thing as before, right? Modulo some like you need to consider the base cases, how it work, but this is the more important part, I argue. So the next question is that what's the time complexity, right? Because now you have a new algorithm, but does it really run in OM plus N time? So formulating recurrences is important. So once you have a divide and conquer algorithm, see, especially if it's a recursive algorithm, what's the recurrence relation to it? Okay, so this is the recurrence relation, the one that you see over here, because I started off with like M and N, right? This is M, this is N, right? Then the smaller region is, just imagine it to be like M over 2 and N over 2. I know there's like plus minus 1 somewhere, but in the grand scheme of things, that really won't affect things. Bit hand wavy here, I know, but let's just imagine it's like half of it, right? Then the OM plus N, it came from the fact that we need to go through this so we need to go through the yellow region. We need to find the maximum in the yellow region. So this is like M time, this is like M time, this part is M time, This part is n time, this is n time, this is n time. So it's kind of like 3m plus 3n to find max. That's where the OM plus n comes from. Okay, so this is the recurrence relation for this algorithm. Okay. Okay, sorry about that. If you hear noise behind. So basically, if you're not sure how to solve like these two things, I suggest like try to solve something similar first. So I propose like, oh, let's see this particular recurrence, right? Tm equals to Tm over 2 plus Om, right? It's just basically this recurrence without the n. Sorry, can you guys hear like background noise? Because like it's quite noisy in my someone else.
Yeah, we can hear a bit, but I think it's okay. We can still
Okay.
hear you. Yeah.
Can. Okay, so please ignore them. So yeah. So let's solve something similar first. Tm equals to Tm over 2 plus Om. Okay. So in case you didn't notice, this was like a quick select recurrence. So if you know the time complexity of quick select, then it's essentially the same. But so I will try, usually I try to use recursion tree or like just expand them. So see this, right? I start with Tm equals to Tm over 2 plus Cm. I expand it. I start with Cm. Next stage is Cm over 2 by substituting Cm to like this recurrence. Okay, wait. So sorry, never mind. I'll repeat that again. Cm, right, is then you expand the Tm over 2, you get something like Tm over 4 plus Cm over 2. So this is where it came from, this Cm over 2 and so on, right? This will be Cm over 8 over 16 and so on. Okay, then this region, basically you can factor out the Cm, just factor out the Cm and notice that 1 plus half plus a quarter and so on is the sum of GP. And hopefully by now, you know, you're familiar enough with the sum of GP formula to know that this entire thing is bounded by a constant. So if it's summed to infinity from like from the 0th power to all the way to infinity, you should get something like 1 over 1 minus r, where r is the ratio, right? So here it's like 1 minus 1 over half. So this entire thing should be like 2, something like that. Okay, so this is how you get OM. Okay, so this is a quick recap. Okay, alternatively, you can also use master theorem, right? So let's take the opportunity to revise master theorem. So we call the steps to master theorem is to first do the log BA, right? So I do log B. So which one is B? Is it 2 or 1? So here, this is this thing, there's this thing, right? Is B 2 or 1? 2, right? Good. It's okay. So yesterday I made an oopsie and I put 2 for both. Log 2 of 2. So yeah. So this is log 2 of 1, right? Is basically 0, right? So case 1 of master theorem compares like the function fn. For now, imagine these are n's. Imagine these are n's because I don't want to like mix up. So fn. So Fn here will be like On, right? Case 1, Fn equals to big O of n. Okay, I'll put the log BA here first. BA minus epsilon. Case 2 is something like if you can show that Fn is theta of n log BA, then log n power k. Case 3 is something like Fn is the theta of n log BA plus epsilon. Okay, so which one of this do you think can work? Which case do you think can work? So we are comparing n log BA equals to like basically n power 0, which is like constant 1. Which case? So okay, I see a stream of 2s. I think it was for before, right? So just say case 1 or case 2 or case 3. Case 3. Okay, I see people saying case 3, and indeed case 3 is right because Fn is like let's just say it's like n lah. Let's say it's n, which is omega of n power 0 remember you have to specify the epsilon, right? So tell me what the epsilon is. But here epsilon can be basically anything smaller than 1. So I'll just put like 0.1 maybe, 0.1. So sorry, it's too close to the borders, but it's like omega of n power 0.1. Okay, so basically this falls in the case tree of master theorem. And you need to check one more thing for case 3, which is the regularity condition. Please check it out, but I won't show it here right now. It should satisfy it as well. And this concludes, case 3 concludes that the answer is theta of Fn. That Tn equals to, so let me box this because the colors are getting out of hand. Tn equals to theta of Fn. Okay, so it concludes that Tn equals to theta of Fn. And basically it concludes, so it concludes that this is theta of n. This recurrence is like On or theta of n. Okay, so hopefully that's a quick recap of master theorem. Yep, and you're able to use it as well. Nice. So any questions? Okay. I think that's the end of the first question. Oh, wait. No, not the end yet. So this is, we showed, this is OM, but we haven't exactly showed what this is. TMN, TM over 2, N over 2 plus OM plus N. Okay, so the third case, no, not the third case, sorry. Now we are trying to solve this, but this is not exactly usable. We can't exactly use master theorem for this recurrence, but we can still use kind of like expand unrolling the recurrence or like recursion tree if you like to think about it. But the working is very similar to before, to like this guy over here. So just expand it, we get m plus n, m over 2 plus n over 2, m over 4 plus n over 4, and so on. Reorganize things. Here I just make it nicer, reorganize the m's and n's. Factorize out the m, factorize out the n. Then same as before, it's a sum of GP. Both are bounded by a constant. So this is OM plus n. Okay, very nice. We have a divide and conquer algorithm. We worked our first solution. The very nice solution is to just basically search the entire matrix OM times n. Then we found a clever idea to divide to recurse only one side. That becomes OM log n. Now we further improve the idea to divide both by columns and rows, and we get OM plus n. Okay, cool. Right, so yep, hope that was a good recap for some of you, like master theorem and things. So next question, please just PM me if you have any questions, but I'll go on. Is expected number of inversions. So this is a past midterm question that I slightly simplified. So the original midterm question has more context to it, but the core of the question is to prove this answer. So now it's a randomized setting, right? You're given a permutation of array which contains distinct elements 1 to n. So for example, like I say n equals to 5, then this is like, this can be like 3, 1, 4, 2, 5, something like this from 1 to n. Okay, the key property here is that it's distinct, right? So there are no duplicates and there are n elements. So an inversion, it looks like mathematically complicated or anything, but it just says that the index I, if it happens before index j, then the element that at index I should be larger than the element at index j. It just means the two elements are flipped. The element that appears intuitively, it means that element that appears on the left side is bigger than the element that appears on the right side. It just means that. So in this example, 4 and 2 are inversions because 4 appears first, but it's like larger than 2. Okay, so this is the context of the question. Just okay, I have examples here actually. So let's say we have the array 1, 3, 4, 2. Then 3 and 2 form an inversion because 3 appears first and 2 appears later, but 3 is larger than 2. 4 and 2 is an inversion because 4 is larger than 2, and so on. Okay, right. So the question is that if you are given a permutation that occurs uniformly at random, so all n factorial permutation of these arrays can occur uniformly at random, what is the expected number of inversions you can see in the array? How many total number of inversions might there be? Okay, So let me see. Okay. All right. So I hope it didn't spoil, but those who haven't thought about it, so try to think about it. Let's say, let me give you like a minute or two. So let's resume at like 9:37, maybe 9:37. So in the meantime, I'll check Archipelago if there's anything. Oopsie. That was supposed to be the random video of the day. Oh, sorry, not 9:37, 16:37. Yeah, sorry. I was thinking of my 9 a.m. class. Okay. I see some questions for after class. So those who ask in the thing, I can talk to you about it later. Okay. Okay, it's 4:37. It's a bit fast, but I hope you can at least form the random variables, right? So you've seen this kind of like randomized analysis a lot. So the idea, yet again, is indicator random variables, right? So every time you see a randomized question, try to think of indicator random variables. Okay, not always the case, by the way, because like coupon collector, a few weeks ago, we learned about coupon collector. It doesn't use indicator random variables, but most things that require to count the number of something, usually it's indicator random variables. So first step, like just think of indicator random variables, see if you can form it. Okay, so analysis pattern, which I keep mentioning this from like week 5. For 3 weeks, you have seen this slide a few times. So try to identify the random variable that you want to count, right? What's your goal? The goal is the expectation of that random variable. Okay, so then express it as a sum of random variables, right? In our case, if we use indicator random variables, I'll say IRV for short. If you use IRV, then all of these are IRVs. All the n things or like how many things are IRVs. Calculate the relevant probability for like x1, x2, and so on, right? Then after you calculate their relevant probability, if you are using indicator random variables, IRV, then you get the expectation for free. Remember that expectation of indicator random variable is basically the probability of its associated event happening. Okay, so after that, use linearity of expectations to add up the sum of random variables. Okay, so recall, our goal is to find the expected number of inversions in the array, right? So let us define the random variable x to be the RV representing the number of inversions. Okay, so the sub-random variables, the sub-indicator random variables, is that the element at index I and j form an inversion. Okay, so visually what you can imagine is that look at this index, maybe this I and j. Do the elements here inversion? Okay, so inversion. So that's the idea of this indicator random variable. It's not the elements, right? So take note, this is the index of the array. Okay, do they form an inversion? So we want to count all possible number of inversions, all possible inversions. So what we do is that we define x to be the sum over all the pairs of xij's, all possible pairs of indices. You ask, hey, this pair, are you an inversion? Hey, that pair, are you an inversion? And so on. Okay, sum over all the pairs. So the next thing we need to do is we calculate what is the probability of xij being 1, right? What's the probability of element at index I and index j form an inversion? This will be enough for us to get the expectation. Okay, then we can calculate ex easily. Okay, you see this for many weeks, so I hope you get up to this far. If you ever like face like a randomized problem, hopefully you get up to this far. The challenge here is finding what's the probability of this. Okay, so when is xij equals to 1? Okay, recall xij is the indicator random variable that element at index I and index j form an inversion. Okay, so when does it also means, like, by definition of inversion, when is it that ai, the element, is greater than aj, right? This is basically the definition of an inversion. So probability of xij being 1 is the probability of the left element greater than the right element, ei greater than aj. Okay, any guesses? Okay, I know I shared the slides already, so maybe you can just shout out the answer, but yeah, 0.5, right? So 0.5 is indeed the probability here. So I remember first time I see this, like I was like not convinced, like how come it's half, you know? But thinking about it, it makes sense. Why? Because remember, your permutation input is uniformly distributed. Anything goes, right? Any shuffling of that n factorial elements, it can happen. And the intuition here is that either one element is greater than the other, or it is less than the other, right? Both ai greater than aj and ai less than aj, they're equally likely. And just recall, the input only has distinct elements, so you don't have to worry about like the equality sign. Okay, so the probability that ai greater than aj is half. The intuition is because both, it can happen like equally likely. Okay, so any questions about this? Okay, I'll just wait for like, okay, thanks. The thumbs ups. So I'll go on. Right. So this is like an example. If you are like you still think, okay, this won't like prove for every general case, but here's an example. All permutations of n equals to 3 is like 3 factorial, right? There are six permutations. And let's focus on the first two elements. When they form an inversion, I count it, right? So 2, 1, 3, 1, 3, 2. So remember, I'm focusing only on the index, the position, first and second element. They form an inversion 3 times out of the 6 times. Okay? So, yep, 3/6, basically half. Okay? So, well, after we get a probability, everything is basically the same thing we have been doing weeks after weeks after weeks. You start off with the expectation of x, then expectation of x is the expectation of all the xij's for all the pairs of xij. Okay? Then after that, you apply linearity of expectation. Okay? You apply the linearity of expectation. Ex basically push the e into this sums. Okay? And then exij, remember, is the probability of ai greater than aj. This is exactly what we just counted. Probability of ai greater than aj is half. So we substitute half here. Okay, then this next part, there are n choose 2 pairs. So that's why it's n choose 2 times half. So you count half plus half plus half. This is basically half plus half plus half, all the way half. And there are n choose 2 pairs. So that's how I got to this line. Okay. Okay, if anyone not clear how you even got n choose 2, how to get even n choose 2 pairs. Okay, so I get some people knowing not knowing how this n choose 2 comes about. So combinatorially, so imagine you have n elements, right? The definition of n choose r is basically choosing out of n elements, right? So n choose r equals to out of n elements, number of ways to form R subsets. Okay, R-sized subsets. R-sized subsets. Okay, so that's the definition of n choose R. And remember, we are finding all the pairs. So like 1, 2, 3, 4, 5, right? So we want to find all the like pair 1, 2, pair 1, 3, pair 1, 4, and so on. Okay, so there are n choose 2 pairs because basically we want to count all the possible subsets of size 2. Out of the n things that are here, out of the n things, oops, I erased. Out of the n things here, right, we want to find subsets of size 2 to a pair of elements, basically. Subsets of size 2. So subsets of size 2, and that will be n choose 2. Okay, so someone asking me, why is it not the permutation, right? So remember, all we care about is individual elements, sorry, individual pairs. We want to count the expected number of inversions. So we ask like, oh, inversion only cares about pairs of elements, only cares about pairs of elements. So how we decompose it is that we consider all pairs of elements. To count all the expected, all the inversions, we ask, hey, you, that pair over there, are you an inversion? Then you ask another pair, hey, are you an inversion? Ask another pair, are there inversions? Okay, so then basically like that's the reason we account for every single pairs. So there are every single pairs is basically well, it's n choose 2. I'm not really sure how I can explain it. But okay, here's another perspective, right? So in case you don't like combinatrix, you hate combinatrix to the core. So okay, I get a PM. Yeah, permutations will kind of like double count it, I guess. Although I'm not too sure what because I only focus on indices. I focus on indices. So it's kind of like choosing pairs of elements. I think permutations. Okay, I'm not sure if you are, when you say permutations, you mean like this time everything times 2, is it? I'm not too sure when you say permutations. No, okay. So I think permutation, okay, just confused. Yeah, so permutation will definitely double count it, right? So, but okay, so in case you hate combinatrix to the core and you don't like using combinatrix, here's like an easy way out that still uses math, unfortunately. So all the way to n, right? So consider all pairs basically like 1, 2, 1, 3, 1, 4, and so on. Then 2, 3. Okay, let me not do it. 2, 3, 2, 4. Like this is all pairs, right? Do you agree with me that this is all the pairs out there? Like if I just continue and so on. So this guy, focus on this guy, pair it up here, pair it up here, pair it up here, and pair it up all the way. Then this guy over here, because I paired it with 1, so I only focus on the things ahead of it. Right? Focus on the things that are ahead of it. So, okay, so fixing 1 on the left side, right? How many pairs are there that has 1 on the left side? Okay. Okay. Okay, I get n, close n minus 1. It's n minus 1, not n. So n minus 1 because you know, like 1 is already considered, right? It's n minus 1. Then how many pairs are there with like 2 on the left side? Enter too fast. How many pairs are there with 2 on the left side? Is it n minus 1? Is it n? Right, n minus 2, right? And I hope you can see like this process goes on, like plus n minus 3, plus n minus 4, plus all the way to plus 1, right? The final pair is like when you consider element n minus 1 on the left, right? So this is sum of AP with n minus 1 elements. With n minus 1 elements. Okay, so the formula for sum of AP, okay, sum of AP with x elements, okay, so I want to put x because I don't want to confuse with the number of terms that we have, is x times x plus 1 over 2. So here we have an AP with n minus 1 terms, which is x equals to n minus 1 basically. And we get n minus 1 times n minus 1 plus 1 over 2. Okay, so I didn't explain how I got x times x plus 1 over 2, but hopefully you know by now, because yeah, so it's just the sum of PP. So this is basically giving us n minus 1 times n over 2. Okay, so in case you know, like you hate combinatorics, you don't want to think about n choose 2 whatsoever. This is like another way you can get this answer that you want. So all that work to do is just saying that this guy is n times n minus 1 over 2. Okay, n times n minus 1 over 2. Then basically we need to times the half, giving us n times n minus 1 over 4. Okay, no problem. Okay, cool. Any questions about this? Okay, so actually that's kind of like the last slide I have. Yep, so slightly earlier today, but I think we went through slowly for some parts, so hopefully you understand. Let me share the slides in the link. Oopsie. Share slides in the chat. Slides. Okay, then afterwards, let's see. I have 2 extra questions. So this is like one random question I thought about during the week while I was like in a breakout room class. I thought, hey, this can be a 3230 question. Okay, then after that, the next question is things slightly more interesting. Cover time of a complete graph. So those who want to think about it, you can stay back. I'll, like usual, I have like 30 minutes consultation session. Then, yep. So other than that, thank you very much. All the best for midterms tomorrow. I think I'll be proctoring some of you. So I guess I'll see some of you tomorrow. The other class actually asked like whether the past slides are accessible. I don't know if you saw, but like the Telegram chat, actually I pinned the slides over there, but for the benefit, I know it's like just less than slightly over 12 hours to the midterms, but let me just share the slides anyway, like the complete set, right? So this is the entire slide. And if you didn't know, like I actually put up all the Zoom recording links over here. Yeah, let me see. Drive. So I put up all the Zoom recordings here. And I actually gave some remarks as well, like whether that particular consultation session had any interesting questions or not. And yeah, basically like it depends whether you which class you're from, and maybe you can see, oh, the other class I did this, right? So yep, so this will be updated like throughout the SEM, like as I prepare the slides for future SEMs as well. Okay, so yeah, and if you ever lose it, but you have one of my slides is actually in the very beginning of the slides also. You can access the same thing via this link. Okay, so yeah. I see someone has finished the cover time question. Okay, so with that, I class is, oh, today no archipelago. Well, I mean, I did put up archipelago, but I didn't need you to fill it in because I don't know if you noticed, but I actually sent the slide answers already to the Telegram group. So I didn't see a point in like asking you to fill up archipelago whatsoever. So the archipelago is just asking, oh, how are you this week? Or is there any like extra question you want me to go through? Oh, no need to fill in. No need. It's okay. I kind of have a list of like who attended the class from the, you know, like attendance of the Zoom also. So fill it in. I think it's okay lah. It's this week a bit more chill. Okay. Cool. So with that, I can dismiss the class. Class is over. If you have any questions, can you go through the extra questions? Nice. Okay, so people are excited for extra questions. So for the 2 people who asked in the archipelago, so I hope you can stay tuned for a bit while I go through the extra questions first. Okay, so any predictions for the first question actually, right? This question is meant to be like, it's not meant to be difficult. Any guesses? So after like 1 or 2 guesses or like people solving, then I can go through it, the rough idea. Yeah, so n over m, great. Everyone's getting n over m. And I hope it's really clear why. And if you think about it, this problem is kind of like the problem of hashing, right? So I have n students. These are like n items. M breakout rooms are like a hash table of size M. Hash table of size M. So assigning uniformly at random, you can think of it as like, oh, xi, define an indicator random variable xi, right? And xi is defined as like the student I goes to like a certain breakout room. So this is the student. The expectation is 1 over M, because it can be uniformly distributed across all the M breakout rooms, right? It can be like over here, or it can be like over here, and so on. 1 over M. And then I have N students, right? N students. So, well, the answer is like N times 1 over M, because I hope I don't need to explain too much why it's N times 1 over M. But yep, so very good. Very good. The second question is the more interesting one. Right. So you don't get how to define xi. So okay, so let me fix the breakout room. In a breakout room, let's call it breakout room number 1. Let's call it breakout room number 1. Like I just fixed a particular breakout room. So xi be the indicator random variable that student I. So they're like n students, right? All the way. I n. I repeat that the student I goes to breakout room, goes to that breakout room. So there are M breakout rooms. And the probability of you getting to this breakout room number 1 is 1 over M. Probability of xi equals to 1 is 1 over M. Is this clear? Yep. So do you see that it follows everything else like n over M? Because I have n students. Oh yeah. So I think yeah, that was the confusion. That must have been the confusion. Yes, no problem. Yeah. Okay. The next question is more interesting. So you're given an undirected complete graph of n nodes. Okay, it's called Kn. Starting from a node, you randomly choose one of the neighbors to visit. And an important note here, which I didn't exactly say for yesterday's class and gave a bit of confusion, is that you can revisit something you have visited. Okay, this like process of you choosing randomly visiting someone is called a step. Then we keep repeating this process. We choose a neighbor to visit it, choose a neighbor to visit, go there, choose a neighbor to visit it, go there, and so on. Okay. Then I say that there's this definition of cover time. Cover time is the number of steps required for you to visit all the nodes in the graph. Okay, so include the step to visit the first one. So illustrating this, let's say I have a complete graph of 5 nodes. Okay, let's say I start from this node over here. So this is step number 1. Okay, I can randomly choose one of the 4 neighbors to visit, either this guy or this guy or this guy or this guy. Okay, let's say I chose to visit this guy first. I choose this guy. This is node number 2. Okay, and this is step number 2, right? Step number 2. Then you can randomly choose one of his neighbors again, including the guy that you just came from. Okay, so potentially you can also come back. You can also come back over here, right? So the third step is spent on you visiting back to the same node. Then maybe after this guy, you visit this guy. Okay, so this is the 4th step. Then maybe you visit this guy. This is the 5th step. Then maybe after this, there's only 1 node remaining, right? But this guy like went to a detour and visited this guy instead. Then this is the 6th step. Then this guy goes over here. Finally, it visits the entire thing. This is the 7th step. And so we say that the cover time for this process, this particular random process, is 7. Okay, is the question clear? Or confused by even the question? Okay, question's clear. Good. Okay, so I am asking what is the expected cover time, because our random thing that's happening is like you randomly visiting, but potentially you revisit something that you have visited. Okay, any guesses? So except for the guy who PM me already. let's give it like 2 minutes, okay, for people to think about it, because I think this is worth like thinking about. Yeah, so someone is asking me, we are expected how many times we hop until we visit every node. Exactly, that's the definition of the cover time. As the number of steps required to visit all the nodes in the graph. No problem. Yeah, you're right. Yes. Okay, so okay, any clues, any guesses? Okay, why do you say n log n? Yeah, sure. Okay, no problem. Thanks for coming. Ah, sounds like coupon collector, right? And indeed, it is pretty much a coupon collector example. Okay, so I opened week 5 for a reason, because the coupon collector is defined here. Why does it sound like a coupon collector? So, okay, where's the coupon collector? So remember, the coupon collector problem, there are n types of coupon that you want to collect. You randomly draw it with replacement. And what is the expected number of times for you to draw all the coupon until you have, basically you have at least one of each type of coupon. How do you model this thing as a coupon collector problem? Basically, the nodes are like the coupon that you want to collect. The node that you want to collect. Okay? Randomly drawn with replacement is basically like you can revisit something that you have visited. Right? So this is how you model the randomly drawn with replacement. Then, well, the goal of coupon collector is collecting all types of coupon. So it's basically visiting all the nodes. Does this make sense? Like this formulation makes sense? The first time I thought I received this question, I was like, oh, wow, cool. Sounds like a coupon. Okay, as in like, I didn't immediately think of coupon collector, but I thought it was really cool how it like, it's almost like a one-to-one mapping to a coupon collector problem. Yeah, so cool, right? So remember coupon collector's answer is like theta n log n for the expectation. So yeah, so the expected cover time is also theta n log n. A small caveat is that you just need, if you do like the analysis rigorously, a small caveat is that in coupon collector, you can, after you collect coupon number 0, or let's say coupon number 2, for example, the next round you can collect back the number 2 again, right? You can collect yourself consecutively. But in this graph model, notice that you can only visit something new. You don't visit yourself. You don't visit yourself, because if you visit yourself means there's a self loop. Unless I allow self loop. If I allow self loop, then this is like exactly a coupon collector problem. But because I didn't allow self loop, you can only visit one of the other 4 neighbors, not including yourself. Okay, so this is just a small caveat, but it's not that hard to fix, because okay, I'll let you think about it. But the fix is basically this probability, right? It's the probability of collecting a new coupon I, or basically visiting a new graph. Instead of it being n, it becomes n minus 1 instead. It's as simple as that for the fix. Okay, So it's n minus 1 instead. So in the analysis, okay, so I said it's n minus 1, and the n minus 1 is located here later on. This becomes n minus 1, but you know, n minus 1 times log n is still on log n. So it's basically still theta n log n. Still theta n log n, but with a smaller value, Okay. Any questions about this? I really thought this was a neat example. I learned it from another module. I'm like, wow, one day if I'm teaching 3230, I'm gonna give this to my students. So I realized my dreams today. Okay. If not, if my dream is to torture students, no, my dream is not to torture students. It's to give you like nifty, cool examples. Okay, so let me see. Okay, so I received the question. How should I do this? Okay, let me create a slide for this. Okay, the first question I received is question 4, part A of term 2020 paper. How is EX deducted? Deduce will do. How should we prove correctness for recursion? For example, okay, so for recursion, right? So if you use invariant for iterations, I'll answer the second question first. I'll answer the second question first. So if we use invariant for iterations, for algorithms with recursion, okay, so to the person who just PM me, can you put it up on Archipelago, because there are some questions queued up there as well, so I can like easily answer your question later on. Okay, so okay, how for recursion you prove it with induction. So like let's say algo n, maybe it looks like algo n over 2, okay, and some base case. So base case, then basically you prove base case. Proof by induction, then show base case first, like show that the base case holds. So basically, maybe you wanna, wait, hang on, let me see. Oh yeah, prove that the base case corrects. Like if you have maybe n size 1, n equals to 1, show that it gives you the correct answer. Okay, then the next step is assume that it solves for k less than n. K is basically the current problem size. It is not yet n, but for something that is like smaller than n. Okay, so depends on induction. Like maybe you want to use strong induction if it's like n over 2, right? Or not regular induction if it's like n minus 1 or something. But strong induction basically shows for all the range. Okay, so right, this is n. This is the region for true by strong induction. The inductive hypothesis. So you show that, okay, assuming that this region is true, right? You make use of that fact to somehow prove that this current step, the n step, is true. The current step we are in, the n step is true. Okay, is that okay?
Yeah. So it's actually when I look at the answer, it's like it's basically iterating it doesn't look like a proof for me. I mean, if you check out the question, if I share my screen.
Yeah, sure. Let me stop sharing.
Yeah.
Okay, basically, okay, for those who asked in Archipelago as well, can you tell me if you need to go off like soon so that I know whether to do your question first? Yeah.
Yeah, so the answer is literally like reiterating what is happening in the algo,
yes,
and this is like
Yeah, okay, I see. Yeah, so I see your concern that basically it's like kind of like repeating exactly what the algo said. So how to argue, right? So
I mean, even the so the correctness and the assumption is this is correct.
yeah, so the inductive hypothesis here, I think it's saying that let's assume that that particular input, the input will give you the correct answer. Okay, so if it's
Maybe it's
Mhm.
sorry. Yeah, sorry, please continue.
No, just go on, because I don't have much value to add right now.
Oh, okay. So maybe it's something like the assumption is T1 to M, the array is like satisfies the requirements, like so every element in the array is the smallest number required, then prove it. I think maybe it's just a trivial example for this one.
Yeah, seems like it might be a trivial example because what it is saying, basically, maybe I would put in a bit more steps. Like maybe for step 5, it says, oh, okay, by the inductive hypothesis, it correctly computes D1 to K minus 1. So maybe I'll talk about like, oh, by definition of like D1 to K minus 1. Okay, wait, let me see. Sorry. So step 5 and 6, I think I'll just keep it as it is because it's correct by the inductive hypothesis, right? Our inductive hypothesis says that the output of select for that input is correct. So we just assume that 5 and 6 are true. I think the more lines I will put in is like line 3 and 4. So line 3 and 4, maybe I'll argue that, oh, because I'm using a linear time select, I'm able to like deterministically obtain the SK of smallest element. Okay, so someone needs to go soon, yeah. Sorry, yeah. So SK of so after after this, I will go to your question.
No worries. Can go through.
So here, how do we find N naught? Okay, so I'm getting a question. How do I find N naught? So I think it's this question 2020, right? Okay, let's go to the answer instead. So it saves some time. Okay, like this example, you want to find N naught. You're asking how do we find N naught? So the definition of big O, right, is basically there exists some N naught, and this N naught or N0 is like your choice. It's wherever you want. So you can kind of like specify. You can even specify 100. You know, if that is to your comfort, you can say N naught is N. Okay, you can say N naught equals like 100. It doesn't matter, right? It's kind of like you say, oh, by definition there exists some N naught. You can even say N naught equals to 100 because remember, like big O, right? The problem of big O is that as the function size increases, right? As N increases, then you only care about some region onwards. It's not strict. Yeah, exactly. There's not only one accepted N naught. As long as you can argue that your choice of N naught, of course, it has to be some reasonable constant. Usually we want it to be small. Like it's valid for like valid for some value. But technically, even if you put like 1000 for N naught, it's not exactly wrong. Yeah, you can choose like 1000 as well, as long as you know it's correct for your definition, like for element 1000 onwards, for N equals to 1000 onwards, this is maybe like okay, this is N squared, this is N squared. Then for the element 1000 onwards, this function is always upper bounded by N squared. So okay, I'm getting a question. So N naught need not be the smallest value where the other functions start overtaking the other. Yeah, it doesn't have to be. It doesn't have to be. So like I think you're asking like, oh, should it be like exactly this guy over here? Should this be N naught? It doesn't have to be. As long as at some point that guy, like at that point onwards, the guy overtakes already. So like the somewhat nice thing about like big O's is that they are not super strict about the constants, right? You can be a bit sloppy and say, oh, and not 1000, okay, and 1000 onwards, I guarantee that the function is is upper bounded. Okay. Yeah, that's nice thing. And in fact, right? Okay, so I'm getting another question. Is it unique N naught and C, or can there be multiple answers? There can be multiple answers. You can choose N naught and C to your liking. Okay, so if we go back to the definition of big O, I think I was gonna say something. Oh, okay. Okay, I'll link this to okay, is the person who asked me. Okay, there's another question I received on substitution method. So I think it's a good chance for me to link this topic to substitution method. Okay, so asymptotic analysis. Okay, so about the unique N naught and 0. Okay, so if you look at the definition of big O, right, it says there exists constant C and constant N naught. Because if there exists, just choose anyone that fits the condition. So it's not unique. You can choose anything you want. Okay, so great. So okay, so Chia-sang, I'll get back to you unless we have to go soon.
Oh, it's okay. We can talk about it at the end. Yeah.
Yeah. So so I'm getting a question: how substitution method and when to apply each type of proof. Okay. So let me. So substitution method is so to recall, just now earlier today we talked about different ways to do different ways to prove the recurrences, right? So one way is for you to use master theorem. Another way is to use recurrence tree, or you can also expand the recursion, unroll the recursion. So I hope this is the correct slide that I'm in. I say that substitution method is like, it's kind of like the strongest tool to use, but it is also the hardest to use properly. So where's the okay, substitution method, right? So substitution method essentially is saying, oh, guess the answer and then check that it's correct. Okay, guess the answer and then check that it's correct. So like, for example, the somewhat sucky part is that your guess might not be correct, like Tn 4Tn over 2 plus n, right? Maybe you guess On cube, right? And eventually you can show that it is indeed On cube, Tn equals to On cube, but it's not tight. It's not tight because there is a better answer by master theorem. We know that it's like On squared. Okay, so this is kind of like the sucky part of substitution method, where you have to kind of first even guess, and you might not even guess correctly. What if like the answer is actually, maybe imagine On cube, then your guess is like On, right? So this is bad, right? We are guessing something that that's not gonna be correct. So this is the somewhat sucky part of yeah, how to guess if you have no idea what the big O might be. I guess I guess I suppose that depending on the question, right? So if you're not given, you can try to expand and try to see like gut feeling what it feels like, because for example, this 4Tn over 2 plus n, right? I mean, you know, by master theorem, this is probably going to be something like n squared, and you are supposed to maybe show by substitution method the recurrence. So it's a bit of a weird hammer if you use n squared directly from master theorem. Might as well solve it in master theorem. But let's say I give you this recurrence instead. 4Tn over 2 plus 1 plus n. This is, well, okay, I think unless you manipulate this into some form, you can't exactly use master theorem. But you can see that by adding this plus 1, your plan to use master theorem might be disrupted. Okay, I don't know if you can use it or not. I think you cannot, because if you expand this, there'll be n plus 2 over 2. And this is not a master theorem form. Okay, but you know, if it's like similar to something you have seen before, then you can make some educated guesses that it's probably something like On squared. Okay, so this is the first step of the guess. Okay, I personally feel it's not reasonable if like prof just give you a random recurrence and say, oh, bound this by substitution method. Okay, I think that will like take a lot of time for you to like make good guesses, especially if it's a funny thing. I only think if it's reasonable if like he say, for example, like oh, use substitution method to show that it's like oh something. Okay, so either that or he even directly gives you the inductive hypothesis. Okay, so the next thing is that if you, after you make the guess Tn equals to On cubed, you cannot say that, oh, inductive hypothesis, Tn is On cubed. That is kind of sloppy. The next thing you do is like you show, you say like, oh, by the definition of big O, there exists a constant C, like this constant C, right? Such that it's valid for some value onwards. Okay, so after that, well, the thing you do over here, right? Assuming this is true, right? First, you guess the base case. So let's ignore all this. I just want to like convey the idea first. Okay, the details you have to like play around with the math a bit. Okay, so okay, here this guy proves the base case where t equals to 1. T equals to 1, and that's valid. Okay, the recursive case, meaning for n more than 1 onwards, what you do is that, okay, this is the strong induction hypothesis. This is the inductive hypothesis. It says that for some value of k, by strong induction, assume that for all value greater than 1, but strictly less than n, then it already holds. Like tk is already less than equals to c times k cubed, which is what we want to prove over here. Okay. Then using this assumption, what you do is that, okay, this is the recurrence, right? 4tn over 2 plus n. So by that assumption, we substitute this into the inductive hypothesis. So you get 4, like TNC, like ck cubed, ck over 2 cubed, something like that, right? Or Cn over 2. Okay, it's basically all here. Like basically you substitute this to the inductive hypothesis. So you get n over 2 cubed plus n. Then you do 4Cn cubed over 8 and 8. Yeah, 8, right? What happened? Did they change this value somewhere? Oh no, it's correct. It's 4 over 8. Then it becomes like Cn cubed over 2 plus n plus n. This is exactly this part over here, which is upper bounded by Cn cubed for some value of that. Okay, so I might have gone too fast, like, oh, I realize how bad yellow is as a color for showing things. But I just want to convey the idea is that you set like some inductive hypothesis which matches your answer, and then you substitute it here. Okay, then all right. So I wanna, okay, did I lose anyone here? Anyone wants me to talk about something first? Because I'm gonna add on a bit more to this. There are some things like which might be good to know. Okay, so first point, related to the fact that big O, right? You can choose your n naught to be anything. You can even, like, remember n naught equals to 100. Technically, it's not wrong if you choose your base case not to be T1, but you choose it to be T100. There's nothing wrong with that. Because remember, we care about the big O. Starting at some point, this time, starting at the point of n naught equals to 100, it's gonna like be like that all the way. So even if your base case is like T100, it's okay. Okay, you don't have to like strictly say it's like T1. One doesn't have to be the base case. Okay, but of course, you know, like we want to show it as much as possible. So usually people strive to make it one as possible. Some people like make it easy by putting T2 or maybe T4 for some reason. Okay, that's okay too, because remember, big O concerns about you scaling up all the way to huge values of n. This is point 1. Base case can be anything reasonable. Okay. So I received a question over chat a few days ago. He was confused, like this Tn less than Cn cubed, right, is derived from On cubed. The fact that it's On cubed. But your inductive hypothesis doesn't have to be C times n cubed. I say this because sometimes the inductive hypothesis can be Tn less than equals to Cn cube, like maybe minus Dn cube, something like this. Or you can also set it up Tn less than Cn cube plus minus 1 for some reason. Okay, so if you come up with an inductive hypothesis, don't be too hung up on like showing it's less than equals to Cn cube. Okay, you can be wrong. You can be wrong. You can use less than Cn cube, but turns out your induction will not work. You realize, oh crap, your induction cannot hold. So does it mean you give up? No, you can change your inductive hypothesis as long as it's still On cube. As long as it's still On cube, you can tweak it a bit, like Cn cube minus Dn squared. Okay, or Tn, it can be Cn cube minus 1. All of these are still On cube. Does this make sense? Okay, so okay. Then third point, right? I think related to the question that person is also asking me, when to use strong induction, when to use like induction and so on. Generally, induction and strong induction, they are kind of like equivalent. You can show that you assume one is true, then you can prove the other, but that's hugely out of scope. But generally, if you see something like n/2, like n/2, n/3, basically not anything that's not n-1, you use strong induction. Just use strong induction. So like here, right? Here our thing is n/2. Then just use strong induction. Assume that everything smaller than n-1 is true as well. But if it's something like Tn equals to Tn-1 plus On, because it's -1, you can use regular induction. That's fine. Probably fine. Okay, but well, I mean, the strong induction has the name strong, and it doesn't come at additional cost of it's kind of free of charge for you to assume that strong. I think it's fine if you just use strong induction all the way. Okay, so the next thing is yeah. So okay. So going to this other point, right? I was mentioning that don't be too hung up on your inductive hypothesis being precisely Cn cube. Okay, so making first the annoying, again, substitution. The annoying part is making a good guess of what the big O answer is. The second annoying part is making a good guess of what inductive hypothesis is, right? Because not only you have to guess this correctly, you have to guess the On squared correctly or On cube correctly. You have to prove, you have to guess the inductive hypothesis correctly. That's annoying. In my opinion, it might take a lot of trial and error. Okay, so well, let's see how I can give like a maybe how you might go about it. So this actually, the lecture slides gave a good example where it says, oh, prove that Tn is actually On squared. Right, we want to tighten it, right? So we want to tighten it. We use strong induction and assume it's Ck squared. Right, this is the definition. Our inductive hypothesis is Ck squared. Okay, then remember the reason. Okay, it follows through everything here, right? It just goes on and goes on and goes on. Then from Cn squared to On squared, this is not correct because we have to show that the inductive hypothesis holds. So we need to somehow show that Tn, if we can show that Tn is less than equals to like Cn squared, then we win, because this is the form of inductive hypothesis that we need. We have to show that we eventually end up in this form of the inductive hypothesis. Our inductive hypothesis is not Tn equals to On squared. The Tn equals to On squared hides too many constants. We have to show that it's exactly Cn squared, at most Cn squared. But you see over here, right? Oh no, no hope, because we get Cn squared plus n, which is clearly like Cn squared plus a bit more, right? So this is what I mean, like, oh no, your inductive hypothesis fails. So what can you do, right? So you observe, hey, this n over here, right? It kind of like makes my thing too much, my Ck squared a bit too much, right? So it over exceeds my inductive hypothesis. So why not, instead of like making it Ck squared, maybe I make it Ck squared minus some value over here. But I mean, I don't know what value it is exactly, but maybe I can guess maybe like minus some number d, this is a constant d, times k, right? So I bring it one level smaller because I realize, oh, there's an excess n over here. Maybe I want to somehow minus n, I want to somehow minus away the n. So guess new inductive hypothesis, tk less than equals to ck squared minus dk. Okay, so this is the constant, right? This is a new guess. Like this is improving your guess because your first inductive hypothesis fails. So this improving the guess. And I think that's exactly what they did here, right? Show that instead of it being cn squared, it shows cn squared minus some constant. So this is the C2k. And that is like how I will go about to work out this kind of like if I come up with an inductive question. In fact, one of the, okay, so some trivia. If you go to the extra problem set, where's the extra problem set? CD additional. So fun fact. Okay, remember this funky question? I don't know if you've seen it before, but so okay, this can be proven by induction. I proved this by induction one day before my own midterm. So sometime 3 sem ago around this period. 3 sem ago? Yeah, 3 sems ago. 3 sems ago around this period, I proved this by induction. I actually struggled to come up with the first good guess of the answer, but my K was like, okay, let me spoil you a bit. The answer is Tn equals to On. But Tn equals to On still means that I have to find a good inductive hypothesis, right? Because I cannot just say upper bounded by Cn. So 2, 3, PF. Okay, so if you see the answer, right, it's going to have like some inductive hypothesis over here, Cn minus C minus 1. Okay, and actually, right, like the one who wrote this answer key this was taken from sometime last sem, and it was like one of my good friends who wrote the answer key. We were both like in front of the whiteboard proving this together by induction. So like this inductive hypothesis was come up by me and like my friend 3 sems ago. so we did like the process. We guessed Cn first. Then we know, oh no, the Cn is a bit too much. We need to eliminate some values. Then we keep tweaking until like we get this nice value. Okay, so I'm getting a question, when do we change the base case like from n squared to n squared minus something, and when do we increase the bound like from n squared to n cubed? So the question I get is like, I think you are asking me like how to change this, right? This to Cn squared minus Cn, something like this, is it? So if you're asking this, then I really feel that it's by trial and error. You see that, oh, this is a bit too much. So you try to reduce the thing. Oh, let me see. Okay, I get what you mean. I get what you mean. So you're saying, oh, this is no hope, right? Cn squared minus n. Should I bother caring about n squared, about it being On squared? Should I increase On squared to On cubed? I think you're asking that, right? Like maybe your first guess is n squared, but you end up with like Cn squared plus n, and you think, oh no, inductive hypothesis fails. So I haven't considered that case before, because all this while, either I already know the final result or not. I guess, hard to say, honestly. You just have to try and error, go by intuition. There's no like hard and fast rule. So this is again the sucky part of induction, right? You have to guess. Okay. Yeah, unfortunate. So I was telling one of my friends, you know, like if in substitution method comes out, right, I think it's only reasonable if two things. Prof tells you the exact answer, Tn equals to On squared, for example. Then all you need to do is find a suitable inductive hypothesis and prove it, right? I think that's the bare minimum he should do if he gives out the question on substitution method. But otherwise, then I feel that maybe it's reasonable also to give like the inductive hypothesis. Although this one is a bit too much already, that kind of like defeats the purpose of asking by substitution method. So I feel that if a question comes out, it should be like, it should give you the answer already, like it's On squared, something like that. If not, you will spend a bit too much time, and I think that defeats the purpose. If something like that comes out without the On squared, then I don't know, will I riot? Nah, maybe not, but but in like, I still feel it's only reasonable if at least he tells you the answer to save you some time from guess and checking the exam. Yeah, so in the problem set, they didn't give you the inductive hypothesis. They didn't even give you the expected answer. So I guess that one's still reasonable because you have like 1 week to solve. Okay, it's not exam constraint. You have all the time to make guess and checks as you need. Okay, so yeah. Okay, so I hope that answers your question. The one who asked this question. Okay, so okay, David is still let me see. Oh, actually, I answered your other question, right? Let me see. Yeah, okay, nice. So I also answered your question. Just nice. Kill 2 birds with 1 stone. Right. So okay, let's get back to Jia Xiang's question. So just now on the inductive hypothesis and the question 4, part A of term 2020.
Actually, I think the question is quite similar to the randomization question we go through this tutorial. So yeah,
okay.
yeah, I kind of get it. It's yeah.
Okay, that's good. That's good. Yeah, great.
It just yeah, maybe I need to understand it more. Like it's more for like I didn't think of how should I. So it's a hashing. It's about hashing, and
Yep.
it's very similar to a breakout room question.
Yes.
Yeah. So I just was confused on how do I get the total number. I forgot it's like the n choose 2 or something.
Yes.
But just now you explained it. So
Yes, and choose 2. Hey, that's great. Glad I went through it. I just remember one thing I want to mention about like in general, right, in this module. So this is the tip I've been giving like students from even before the SEM start, like people who are taking 3230, going to take 3230, is that inequalities are your friend. Okay, so like you see this over here, you spam inequalities. Don't get too hung up on like being equal. Okay, this is my own mistake last time. Like I'm always like I always wanted to be precise, exactly equal. Okay, but oftentimes if you just allow yourself to relax a bit, don't put like exactly equal. You put inequalities like this one over here, C2 over NQ plus n. You allow some inequalities. I mean condition on some value, of course. Okay, actually this is fine because like this one over here, right? Cn cube over 2 plus n is upper bounded by Cn cube over 2 plus Cn cube. Actually, no, this is, no, sorry. This is upper bounded by Cn cube over 2. So this part, I upper bounded. I start from n, I multiply by Cn squared over 2, right? I multiply by Cn squared over 2. So we get this part. Then this is equals to Cn cube. Like this is how you show this part. And inequalities are convenient because you allow to be a bit sloppy, but the answer is still correct. Okay, so just a tip in general for 3230s, like proving these kind of things.
Maybe I can ask if no other questions, can I ask like one more or yeah question?
Go ahead. Yeah.
Yeah. So like it's I think it's a small one. So if I share my screen, so for this one, I think they use telescoping, which is out of
yeah.
But I'm just not sure like from this step to this step.
Okay. Yes. So I can explain now. So okay, this is another thing. Like remember what you've been taught before. So like theta of log of I'll put x log of okay wait. Theta of log of x factorial is
an x log
x, correct?
Yeah.
So what happened here to here is basically substitute x equals to log n.
Oh.
Okay.
Oh, okay.
You notice that?
Oh, yeah. I think.
Okay, let me write that for completeness. So log n factorial, right? Then this is equals to log n do you see that? This is this part.
Yeah. Okay. Yeah. So I think I get it. Yeah.
Nifty.
Okay. Yeah.
So you can even have something like, now you can solve something like, oh, log of n squared factorial. Just substitute, you'll get like n squared log n squared, which is n squared log n, like in the theta form.
Okay.
Now you have all the power. And okay, so related to this also, right? Remember harmonic series, like 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 and so on, right?
Yeah.
Until 1 over n. I say that it's theta log n. Okay, this is from past tutorial. So technically, if you change n to something like 2 power n, for example, right? This will become theta of like log 2 power n, which is like theta. Well, this is what's this? This is n. This is n. Yeah, n times log 2, which is 1. Log 2 is 1, so it's n. So nice.
Okay. So maybe another question is like if somehow we didn't get a theta answer, for example, maybe not this one, but
Yep.
like if in this case, because sometimes when we are using this sum, right, we may want to use maybe like a GP. So we assume to get a result, we may extend this to like from log n minus 1 to infinity. So in this case, we need to change to a less than or equal sign, right? And actually, it's a less than sign. So in this case, we can only get like a big O. So
Yes.
so if we give a big O answer, like is it like partial marks or something?
I believe yes. I think it's only reasonable to give you partial marks for that.
Okay, since there's a more tighter bound.
Yeah, if like we know there's a more tighter bound that by right you are able to give it like in syllabus, then I think it's only reasonable to give you partial marks if you give like a big O answer. So
okay,
if you can get exact, it'll be good. But I mean, if you have no clue, then the least you can do is to big O it.
Okay.
Yeah.
Then sorry, I think another one is I'm actually not sure why. So why they like in this tier they did. I mean, it seems to me that they didn't add the last level in. Like there are log n levels from 0 to log minus 1, which is the second last levels.
No. So I think it's there are log n levels, right? So okay, how many numbers are there from 0 to 3?
4. Also it's just nice that when it is just okay.
So this is like level 0, level 1, level 2, all the way to log n minus 1.
So it's actually included in the sum.
I think it's included.
Okay.
Yeah. Okay. So yeah, I still have a few more questions. I think it's fine.
Thanks. Yeah, that's all. That's all for me.
Yeah.
Thank you.
Yep, no problem. So let me answer some of those again. So 2 questions. One is on the lower bounds. Okay, I think I won't talk too much about the lower bounds. I'll just answer the combinatrix question that you were talking about earlier. But I think combinatrix, because that one is not too much in syllabus. So okay, I mean, you still need to know that if you're proving the lower bounds. But let me see, midterm, right? So no, not midterm. Additional practice problems. Midterms. Open 2017. Oh, I had it open already. So just now, so I think this one, okay, I won't go through it also on the basis that I am not 100% sure yet, but I was trying to show like if you have k buckets, this is now combinatrix. Okay, so go back to like CS3230 realm, right? I want to distribute that into the buckets. Okay, so how the perspective to do this? The perspective to do this is I think in 123 it's called like stars and bars method, or I learned it in maybe combinatrix and graph, but you should have seen something like this in 1231. Is imagining each bucket as like a partition. Okay, I'll just imagine this is 2 buckets. Okay, so let's ignore these 2 buckets to make it easy, right? So maybe I want to put 5 things, n equals to 5. So notice that this can be like something like this, right? Wait, give me a second. Oh, wait. Oh, sorry. I think it's not 3. Okay. Sorry, it's if I have 2 buckets, right? You can imagine it as like one partition here, then n equals to 5. So you distribute. So if the partition looks like this, then it means all the 5 items goes to the bucket number 1. Okay, if like there's some other combination, right? This means that 4 elements go to bucket number 1, 1 element goes to bucket number 2, or maybe the partition looks like this, something like this. Okay, so basically, okay, do you see how this maps? How this like me having like bars and like dots, how it maps to the bucket. Okay, so you see this, right? So, but this is essentially what it's saying is that out of like 6 things, find one position to put the bar. Right? So there are 6 possibilities, right? So 6 because there are 6 items. Yeah, it's like where to put the bars. So once you put a bar here, right, the balls go everywhere else. Like basically just distribute the balls anywhere because it's distinct. It's what's it called? It's indistinguishable anyway. Okay, so okay, so basically if I have k buckets, meaning I have k minus 1 partitions or bars, let's just bars, and n balls, right? Yep, it's where to put the k minus 1. So out of n plus k minus 1, because n balls and k minus 1 bars, I choose where to put the bar, and there are k minus 1 of them. So that's how you count like how many ways to put n balls, n indistinguishable balls into like k distinct buckets. Yeah, cool. So my idea initially was to use this idea somehow for this question, but I think yeah, I'm not too sure, and it might take too long for me to like figure out if it's really the case. So okay, the caveat is that in this example, right, it's possible that all the partitions contain the balls, right? So this is 0 and 5 elements. Okay, so because of that, then remember I thought of this because they say we have k distinct elements, right? So if somehow one of the elements, so I imagine a bucket being like a distinct element. This was my thought process. Then basically if one of the elements have 0 elements, right? So one of the indices don't go to this bucket that I want, right? The trouble comes because well, you know, like there's no element. That means we don't have k distinct elements anymore. Exactly. So the hack here is basically instead of considering n elements, right? You consider n minus k. Why n minus k? It's putting all the k elements into the individual buckets first, ensuring that every single bucket has at least 1 element. So from the formula, right? So from the formula, I substitute n equals to n minus k. I hope this is not a confusing notation. I'm talking about this n over here. Then I should get like n minus 1, k minus 1. Choose k minus 1. Okay, so I think this is kind of like the approach. Then yeah, so this is kind of like sorting the k distinct elements. I feel that maybe there's like a times k factorial here later to shuffle the k distinct elements. I feel, but I'm not too sure. Something like that. I have to think about it more. I realize as I'm explaining, maybe there's some inaccuracies. But I mean, hopefully this is a combinatorics revision that can be helpful, not even just for this module. Okay, so I always forget the formula, but I keep thinking of like stars and bars and rederive it every time. Okay, so nice. So, okay, so I had one more question. I'm not sure if I want to go through it because it's the practice problem set. Practice open solutions to. Okay. Whew. Right. So is this question from the practice problem set? Okay. So I am not too sure if I want to go through this because honestly speaking, this is like a really difficult question and it really takes a long time to understand this. Okay, who wants me to go through? Like I can go through, but I'll tell you that returns of investment to this question, I think it's very low. I doubt something this hard will come from midterms. I can go through it. but if you want me to go through it, I can still go through it. But again, midterm is like 12 tomorrow, 11:30 tomorrow, right? Do you want to like visit this or revise other topics? The choice is yours. As in like your revision time, it's the opportunity cost here. So if no one says anything, I'm just gonna assume no one wants to go through this, which I'm fine also. Because honestly, I need to also think. Okay, meantime, okay, since no one is saying anything, I'll assume it's okay not to go through. But any other final questions for other topics or other questions? How to not fail? How to not fail is by writing correct answers. How much money do I need to get an A? I think you need to ask prof for that. I mean, I'm not in control of your grade. I don't think I'm even grading your midterm. So can you pay me to do your midterm? No. I'll be fidgeting anyway. So I can't do BA at the same time. You guys, yeah. Your attendance is taken. Don't worry. No problem. So I'll just stick around until like people has left. Then I'll close the session. It's dinner time. Enjoy dinner, guys. Oh, this is like the latest I have stayed back. Like, and there's so much attendance also. That's nice. I guess it's the midterm effect. No problem. Glad I could help. Okay, nice. Everyone's left. So let's close the session.